super resolution using deep learning.
As a refresher from my proposal, the problem of super resolution lends itself well to deep learning because most of the readily available upscaling solutions tend to produce blurry images and details tend to get lost. So we wanted to explore the use of deep learning to help in preserving or even enhancing the detail. There have been a number of attempts at building deep learning architectures for the purposes of super resolution, but by far the most influential attempts to the field and to us have been these two papers. So SRGAN was a seminal architecture and it used GANs to produce high resolution images. But where they stood out was not in the use of their GANs, but more so in their objective function. Rather than just looking at pixel by squared error, they used what's called a perceptual loss function. It's actually quite a bit involved. It uses a VGG network, which itself is a deep convolutional network that was used more so for image classification. But here they use it as what's called like a perception module, where basically each layer in the VGG activates based on different things that are happening in the image, different features within the image. And so srgan would index into VGG and compare the output of a particular layer between the real and generated images and calls that difference the perceptual or perceived difference. ESRGAN built on what srgan had and enhanced on particularly the objective function and outputting probabilities by the discriminator rather than just binary values. And for the objective function, they made it more robust and sort of more sensitive to fine details. And this helped with having less haloing or bleed around areas of high contrast. And according to the authors, built more natural looking super resolution images.
For our dataset, we chose to use the div2k dataset. The dataset consists of 800 training images, 100 validation images, all of varying sizes. Due to memory constraints, upscaling the entire image in one go is essentially impossible. As a result, we chose to crop a 360 by 360 middle portion of the image to use for our training as the ground truth. We then subsampled the image to 90 by 90 as our training data. Lastly, we ended up splitting the image into 3 separate images for each color channel.
For our implementations, we first wanted to build a GAN network that was inspired by ASR GAN and see if we can improve upon it. One thing to note is that from what we can find, ASR GANs seem to be intended for a 4 times resolution upscale in both the height and the width. But what we hoped to do was to upscale by 2 times the resolution twice to achieve that 4 times upscale, and hope that this sort of spreading out of responsibility can result in better images, but also would allow us to add layers after that first upscale to enhance the features before being upscaled one more time. But sadly, our GAN attempt failed. It produced noisy images that converge towards black, kind of like the image that you see on the right. That's one of the training images. And so we moved on to trying to build upon existing ESR GAN implementations and modifying that to meet our needs. But they really seem to be hard coded at 4 times upscale, and changing that caused weird issues like color being off, or also like black images or noisy images. And so we tried to rethink our approach. We looked at autoencoders next, where we encode the low resolution image to an even smaller image to sort of really highlight the features, and then decode that to the 2 times upscaled image. But that also resulted in noisy images and colors kind of being washed out. So then we moved on to CNNs. We looked into combining layers that can enhance features and also layers to upscale the image.
While working on our implementation, we came across numerous challenges that really inhibited our ability to come up with the best model possible. The most significant challenge we ran into was simply memory. Since we required GPU acceleration, we were limited to about 8 gigabytes of VRAM. As such, we had to be very careful with how we represented our data and weights. This is the primary reason that we chose to separate a color image into 3 separate color channels. If we had a fully connected layer that mapped a 90 by 90 color image to a 180 by 180 color image, we were looking at a weight matrix that was 35 gigabytes in size. The issues that arose with memory allocation made it very difficult to come up with an architecture. Simply choosing how many inputs would go into a fully connected layer was important. Since our output needed to be larger than our input, we needed a significant number of features to work with, but those were incredibly difficult to pass through a fully connected layer. In addition, despite finding architectures that would fit into memory, training time was still very significant. For our final model, using the 800 training images took around 1 minute per epoch. Due to the number of epochs it would take to determine the viability of an architecture, we were only able to test a portion of the architectures that we thought were possible. Lastly, even with functional architectures, there was quite a lot of tweaking of hyperparameters. Adjusting things such as batch size, the number of epochs, and the learning rate had a significant impact on our results. Due to the training time, exploring a large combination of hyperparameters proved to be very difficult. Lastly, we had a hard time coming up with an objective function to use and how to weight them. This was simply another factor to consider alongside everything else. The final architecture that we came up with was implemented using Tensorflow. The final design can be seen in the diagram below, which I will walk through. It's important to note that we settled on the mean squared error objective function to determine how well an output performed. In addition, note that each convolution layer's output has a real activation function in the diagram below. From the input layer, we perform a nearest neighbor upscaling approach to upscale the image 2 times, which essentially results in an image twice the size with no additional details. We then attempt to extract some features using a convolution layer with 16 filters, a kernel size of 5, and a stride of 2. This is followed by max pooling in order to extract sharper details. We then perform another convolution with 16 filters, a kernel size of 3, and a stride of 2 to extract features from the sharp details. Next, we have a dropout layer with a frequency of 0.3. This layer is responsible for randomly zeroing out inputs, and the purpose of the layer is to prevent overfitting. We then flatten this output and feed it into a fully connected layer and then a ReLU layer. From this point, the architecture essentially repeats itself, with changes only to convolution layers. Rather than using a stride of 2 and 2, we change it to be a kernel size of 4 and 3 respectively to account for the fact that the image is now larger.
After training our model on the div2k dataset, we were overall very pleased with the results. As you can see from the images below, the textures on the building were still maintained, and the text was still very readable after upscaling. Though, as you can tell, the colors were not as accurately represented as an ESR GAN. This, we believe, is most likely due to the fact that we were training on all 3 color channels individually rather than the whole combined image at a time, due to the previously mentioned memory constraints. Compared to our training results, our validation results are overall very terrible. Even compared to the ground truth and ESR GAN, our image is nowhere near what it should look like. Overall, the colors are seemingly there, though the overall shape and detail of the image is just not apparent at all. When discussing our validation results, we came up with a few ideas of why it did so terribly. At first, we thought we might have had a saddle point where we weren't producing the overall most optimal results. Though after using Atom and training for a very long time, we realized that this is not the case. It could also be due to the nature of breaking up the images into their individual color channels. Though, with our memory constraint issues and the size of our images, we had no way to really test if this was the issue. It's also possible that the cropped images don't provide enough diversity, and that the model can't distinguish the true results or the true details of the image. But overall, we do think that just the div2k dataset with its 800 training images is just purely too small. If we were to continue this project and continue the research, we would recommend using the HoloPix 50k dataset instead, which has 49,000 images to train on, and should overall produce a much more generalized result, which should produce better images in validation and training overall. Some improvements we can make to our model would be to incorporate SRGAN's perpetual loss objective function. As they mentioned in their research, using multiple objective functions overall improve the results as compared to just relying on mean squared error. Another implementation we could pursue is including spatial pyramid pooling to intelligently extract areas of interest within an image rather than just center cropping. We could also use it to help classify an image and use multiple models then to upscale based on certain features in an image rather than trying to use a single generalized upscaler for the entire image. We believe it would also be best to avoid separating the image into individual RGB color channels and instead training the model on the entire image instead, to avoid the color banding effects that we saw in our previous training models. Also, trying to upscale the entire image at a time rather than blocks or sections would be the most ideal circumstance, as this could pertain to any generalized image and any shape, rather than needing all the images to be constrained to a certain size or dimension.
Here are the references we used for coming up with the design and comparing our results to other implementations. Thank you for listening to our presentation.